The next question, we have a magnetic field of 0.002 Tesla times the vector 2I plus 3J. And of course that vector is larger in magnitude than just the I vector or the J vector. It's going to be about, what is that, square root of 13, about a little more than 3.6 or 3.7 times the magnitude of the I or J vector. In any case, we have this magnetic field, and we have the circle x squared plus z squared equals 4 square meters. Now I call that a circle. What is the shape of x squared plus z squared equals 4 square meters? Well, if you're confined just to the xz plane, that is a circle. More generally, since we're kind of in a context where we're in three-dimensional space, that would be a cylinder parallel to the y-axis, because y would be arbitrary. We'd have this same circle for every value of y in a plane parallel to the xz plane. And of course, I say this because I really want you to get your thinking into the multivariable calculus mode, because it's going to be very important for the next couple of weeks. Okay, so that's going to be a cylinder, but if we cut it with any plane parallel to the xy plane, it's a circle centered at the origin, radius of 2 meters. And I'm not going to explain that. That's something you should simply understand. And if you don't, review your multivariable calculus, quadratic surfaces, vectors, everything. Okay. Now, this magnetic field with this circle, we want to find the flux of this magnetic field through this circle. So the normal vector to this circle, depending on, again, how the circle's oriented, could be either plus or minus the j vector, because again, a circle in the xy plane is going to have a normal vector in this direction or this direction. So the A, I'm just going to let A be 4 square meters times j, and just arbitrarily choosing the plus at this point, and then we calculate the phi b. Well, that becomes very simple. The j dotted with the j gives us 3. The 4 square meters times the 0.002 Tesla is going to give us 0.008 Tesla meters squared, and we multiply that by the 3j, and I don't know why I wrote j down there, because we no longer have the j vector. Okay, the j dot, the j just gives us 1, and we end up with 0.024 Tesla meters squared. Okay, now we want to look at the same circle, but this time we are going to let the circle rotate, and we're going to have the circle be, well, same circle. I'm sorry, I'm not going to have the circle rotating. In this case, we're going to have the magnetic field fluctuating. Okay, magnetic field is going to fluctuate according to the cosine of 100 pi t. Now, when I did this in class, I kind of suppressed the units. I mentioned them. This would be 100 pi radians per second. So the 100 pi means 100 pi radians per second. In class, I did point that out here. And t, if t's in seconds, then the product is going to be in radians, and it's just an angle in radians. We can take the cosine of it, and we should know, in terms of the circular model, how that works out. Okay, so here's our magnetic field, and we have the area vector. Okay, I was just kind of reviewing. Okay, we have the 4 square meter circle in the positive x direction, in the xz plane, or plane parallel to the xz plane, and we have the j vector as the normal vector. So that the magnetic field is going to be, well, you can see the calculation. I'm sorry, the magnetic flux is going to be this dot product. J dot J is 1, so we just end up multiplying with 4 square meters by the 0.005 Tesla to get 0.02 Tesla meters squared. And then we have the cosine of 100 pi radians per second times t coming along. So we have this fluctuating flux. I don't know where I know where that came from. We have this flux, and the flux varies according to the cosine. So it's going to go from positive 0.02 Tesla meters squared to negative 0.02 back to positive 0.02, passing through zero every time. And if we graph the flux, we're going to have just something very similar to what we saw on the last picture, but for a different reason. Okay, now, what's the EMF? Well, I tell you that the EMF, the electromotive force, the voltage induced in the loop, is going to be the negative of the time derivative of the flux. Okay, so the negative of the time derivative of the flux is what? And I think I got careless with signs again. I put the negative on here, forgetting I had a negative here. The derivative of the flux is the negative, well, first of all, it's going to be negative 100 pi radians per second, multiplied by the sine of 100 pi t. And it's going to be negative because the derivative of cosine is a negative of the sine. Since I have a negative here, I'm going to have a positive here. So both of these should be positives. And that's going to reverse my graph. Okay. In any case, it's a straightforward derivative, and we get 2 pi Tesla meters squared per second times sine of 100 pi t. The 2 pi comes from a chain rule, is going to give you the factor of 100 pi out of here. 100 pi multiplied by the 0.005, the 0.02 Tesla meters squared. And of course, we're taking the derivative of this expression, which is the same as this expression. Okay, is going to give us 100 times 0.02 is 2. So we're going to end up with 2 pi Tesla meters squared per second times this sine. And a Tesla meter squared per second is a volt. So that we end up with 2 pi volts times the sine of 100 pi t. 2 pi is about 6, so this is a little over 6 volts, fairly typical voltage for a low voltage circuit. Now, if I want to graph this, I originally graphed it for the negative here. It should actually be the positive. So the correct curve would be this one. Okay, and I could kind of erase this one. But if you just focus on the color, you see that we have this sine curve. What are the characteristics of the sine curve? Well, I've labeled them here. But the amplitude is going to be 2 pi volts. And again, you should know very, very well at this point from differential equations, from previous mathematics, and from previous things we've done in this course with simple harmonic motion and waves. You should know that this is going to have an amplitude of 2 pi volts. So we have 2 pi here. We're graphing electromagnetic force in volts. So we have an amplitude of 2 pi volts, and we have what? We have an angular frequency. Okay, how do you get the angular frequency? You can try to memorize a formula. I don't recommend it. You have the circle, the unit circle picture. The sine of 100 pi t corresponds to an angular change of 100 pi for every unit of t. So for every second in this case, we go through 100 pi radians. Each circle is 2 pi radians. There are 50 2 pi's in 100. So the circle, we go around the circle 50 times a second. We get an angular frequency of 100 pi radians per second, then gives us a frequency of 50 hertz. And we get that from the reference circle picture as opposed to an equation we're going to get mixed up with a lot of other equations. Okay? Or formula. You don't need a formula if you understand the reference circle picture. And the reference circle picture can reinforce what you do with a formula if you do use a formula. Highly recommended. Okay, picture's much easier to remember than where the 2 pi's go, numerator, denominator, or is it 4 pi, or is it something else? In any case, right there's your picture, and the frequency is 50 hertz, and that means, of course, that one cycle takes 1/50th of a second, so that right here is 0.02 seconds. And that 2 got smudged because I wrote a 5 because I was looking at 5. Still smudged, but maybe a little clear. 0.02 seconds here. Okay, so we can visualize how quickly the voltage is oscillating here.